So now we're going to move into the autonomous vehicle segment of our programming. We'll kick it off with our keynote speaker, Kyle Vogt, who is the Chief Technology Officer, President, and co-founder of Cruise Automation. Welcome, Kyle.
All right, everyone's here. Looks like we're awake. Thank you guys for having me. This is going to be an interesting talk, I hope, for you guys. I want to start by saying I think this is a really interesting time to be alive because we're at this moment where you have this convergence of growing compute capabilities. We're just on the cusp of some really interesting things happening in ML. And I really think we've just barely started to scratch the surface of what's going to happen when we take these systems and apply them to real-world problems. I'm here, and I'm going to talk about autonomous driving because I think that's a big one and a really important one for a number of reasons. So you can see the name of my talk there. A big thing here is machine learning is a key enabler for autonomous driving. But first, I want to talk a little bit about some of the things that it takes to actually make that happen. So this slide's got some sort of vanity metrics. They're not really that important for a business. Lots of people. And what's not on here is we've raised lots of money, like $7.5 billion in the last year or so. And I'll tell you why that actually matters. It's a big number. And sort of as a general note, what I'm kind of excited about right now is, to really move the needle in some of these ML problems, it takes a lot of capital. And that's hard to do if you're a small startup or a small company and you want to change something. But in transportation, that's like, it's like the air we breathe. It's like where we live, where we eat, moving around wherever you go, whether it's like to a job or to go to the store to buy food. It affects everyone's life. And because of that, it's an enormous business opportunity, which means there's lots of money flowing into the space, which is great because it means that, like you see academia sort of focusing towards this industry because once people graduate, they want to get jobs in that space. And what that's doing is it's creating this very nice feedback cycle where the money flowing into the space is generating more innovation and more research, which is pushing the industry forward faster than it would without that. So that's really great. So we're Cruise. You may have heard of us, but we're in San Francisco mostly with our autonomous cars. Our goal is just to get these cars out there and at scale, and that's sort of why we exist. But the real reason for that is we live in kind of a barbaric world today, if you think about it. There's 100 people dying per day in car accidents, and obviously that's not what people talk about on the news. There's lots of other things that sort of take our mind share. But this is a horrible problem. Car accidents are the #1 killer of teenagers in this country, which is kind of insane. And I was thinking, like, how do we end up in this place where we have cars that are killing our children and we're not really talking about that much? And I think the reason, maybe it's kind of obvious in hindsight, is that there's no alternative. You are stuck buying a car and driving a car, and there's no other way to live your life without it. And so you have to subject yourself, you and your family, to this terrible existence we have today. And so I like to think of Cruise as existing to correct this. And personally, I can't think of, I haven't figured out the meaning of life yet. I think Greg Brockman from OpenAI is going to be here later today, and he's building artificial general intelligence. And I'm pretty sure that thing will eventually tell us the meaning of life, or might just spit out 42 as the answer. But either way, until we figure out the meaning of life, I can't think of anything better to do than try to fix this thing that's horribly broken, that's hidden in plain sight, and that no one really seems to be doing anything about. Just to elaborate a little more, I have a 14-month-old kid, so this like killing the children thing really resonates with me. And if you think about what parents have to go through today, when a kid turns 16 and they need to get around, like go to school, get a job, whatever, you have to get them a car, or at least most people give them a car. They all want to use Uber and Lyft these days, but most of them still need cars. And I was doing the math on this, and when there's a SUV, like a 2,000 kilogram SUV going 80 miles an hour on the highway, that thing is storing as much kinetic energy, more kinetic energy than a stick of TNT, a stick of dynamite. So it's 1.2 megajoules of energy you're handing over to your 16-year-old kid and saying, have fun. I mean, would you give them a stick of dynamite for their 16th birthday? That's basically what we have to do today. So this is not good. I think we can do much better. So our goal is we want to build some technology that solves this problem. Sort of the minimum the minimum table stakes here is you got to put a product out there that does good. So our cars have to be better drivers than humans, safer. And we believe, just from a sort of moral standpoint, we're going to make the cars of the future be clean. So they're all going to be electric, which means down the road maybe they can all run on sustainable energy. And there's some other peripheral benefits too, but I think that the safety one is sort of the wake-up call for people. We really need to solve this problem. So I want to talk about cars for a second. This talk is about, this conference is about the future of computing, but I got to talk about cars for 1 second, because if you're an engineer, this is really impressive stuff. Like, just to build a car, put this thing together. Those robots probably have some machine learning. Technologies behind the scenes there, just in the automotive side of things. And I was doing the math on this too. To build a car, right? If you want to solve this problem, you got to have cars. You can't just bolt sensors on an existing car. That doesn't work. So if you want to build a car, what does that mean? It takes roughly 1 millennium year. One millennium engineer year of time. Basically 2,000 engineers for a year, or 2,000 years for one poor engineer to build a new car. And that's for like a big car company, like GM or others, where they've already got the assembly plants, all the engineering expertise in-house, they've got the supply chain, all that kind of stuff. It still takes them 2,000 engineer years of time to put a new car together, and at minimum $1 billion. So it's like very capital intensive to solve this problem. So this is a money piece there. But I think, again, going back to the fact that transportation is so huge and the opportunity is so big, it means we're able to bring in enough capital to really start to chip away at some of the really tough ML problems and even take them to the next level. I think you might see some of the greatest innovation in machine learning and computing technologies driven almost entirely by the autonomous driving sector. And that's mostly because the demands for the technology are so extreme. And it's one of the few places outside of like serving up ads to people where there's that kind of revenue opportunity. And so I think that's a beautiful convergence of sort of a business opportunity and one that can have impact. So again, in terms of meaning of life, it seems like a good thing to do. I want to show you a little bit why ML matters for self-driving, because like when I was 13, I worked on my first little prototype self-driving car, and in my head, I think the problem is simple. You build a system that like looks for the yellow lines on the side of the road. Isn't that convenient? There's 2 bright yellow lines that you can pick out of an image and try to drive the car. And then of course, getting into this problem, you see it's much more complex. So here's a video from one of our cars, if it loads here. And basically what I want you to pick up from these scenes is the complexity of the scene. Oh, went right through that one. Okay, maybe. Okay, maybe we'll get the second one. Okay, I'll do this old school. Oh, there it goes. Okay, great. So what you see about this road is there are no lane lines, and people aren't really parked in any particular orderly fashion, and they're not even staying on their side of the road. And then there's these little social negotiations where you have to choose who goes first. And then in this case, there's actually a section of the road that's so narrow that you have to, like, you can't even squeeze by at the same time. You have to like squeeze next to each other, and then the other person goes a little bit, and then there's a little more space, and then you go, and then they go. And all of those things are like not easy to draw it on a whiteboard and say like, if this situation happens, do that. Because your whiteboard would be like, you need like 10 billion whiteboards to capture all the possible scenarios that you could have. And so to do this thing, to like solve this problem that has this huge impact and is going to save the children and all that good stuff, we need ML. We can't do it without ML. And so that's kind of nice that we get to work on these things. Here's another one. I will try to give this one a second and see if it plays. There we go. So other things like the problem with autonomous driving is you don't have this structured world. There's often not lane lines, but then also you have really unpredictable other agents in the universe. And there's these social constructs like people holding stop signs. That usually means like don't run them over and wait until they turn the sign to slow, and then you can proceed. And so like figuring out the context of this situation, like what is the intent of that person holding the sign? As they're waving, are they waving at me or other guy? Like which way are they looking? And when they're waving, which lane are they telling you to go into? These are extremely complicated perception problems. And I think each one of those in itself is sort of a, maybe a PhD thesis or something like that. But certainly a really challenging problem. And so with autonomous driving, like the reason, there are so many people working on this, and we have 1,500 people in this company, and we're only getting started, is the bar for launching is really, really high. Like if you want to beat humans are actually really good at driving. We don't make catastrophic mistakes that often as human drivers. And so if you think about it, you've got these like 3 critical ingredients that have to be all nailed to make this work. You've got basically beating humans at a really challenging task, much harder than chess or playing video games or things like that. You see these unstructured environments. You also have to do it in real time. You get maybe 100 milliseconds to make a decision about what's happening there, which drives sort of insane requirements on the computing side. And it's safety critical. You basically can't make mistakes. Or if your ML system makes a mistake, you need to have a backup system and then probably a backup system for that backup system because people are trusting their lives to this. So that kind of makes this the challenge of a generation. And I think, I think this has been said before, but the closest analogy I can think of to this is the Apollo program. But instead of that being about like sort of national pride and being first, I think in this case, we're trying to like really solve a problem that exists and is hidden in plain sight and is pretty horrible. So to get there, like to solve these problems, you see the complexity of the scene. They're so diverse and there's so many different situations. You need machine learning at scale. And I think that presents a few interesting challenges. And there are only really a few companies in the world that are, I think, forced to do this kind of scale and really need it, and then are able to do it. So I want to talk about some of the little interesting things hidden in there in the scale side, and then what's coming next, like where I think we'll be in a few years from now. So some of the critical ingredients for ML at scale and autonomous driving, we're kind of bootstrapping the system if you think about it. We have lots of cars driving, collecting lots of data. That is a good source of information from which we can build our initial models. I think of it as bootstrapping. At least today, the predominant way to turn data, which is kind of useless by itself, into insights or improvements to your model is by labeling it and saying, this is what that person was doing, this is a car, this is a human, this is a stop sign. Which, if you have a really large amount of data, that's actually a lot of work, a lot of people involved or a lot of tools involved. And then you have kind of, in this case, the data sets that we're working on are enormous. They're not like click streams like you have at maybe Facebook or Google, where the information you're building a model on is where someone clicked on a page or what the order of the search results were. We have vehicles that generate gigabytes of data per second from over a couple dozen cameras, high-resolution LiDARs and radars and all these sensors. And so just the pure infrastructure required to move all that data around, we're talking gigabytes per second per car times hundreds of cars, it adds up really quickly. So there's sort of some fun problems in there that need to be solved along the way and nothing that really does it off the shelf. And then training infrastructure and evaluation tools. This is part of the workflow that a machine learning engineer goes through when they say, okay, I have a problem and a bunch of data. How do I turn that into a system that solves that problem? We talked a little bit about the fleets and the richness of that data. And the reason we want lots of data and lots of driving is to try to maximize the entropy and diversity of the data sets we have. If you think about it, if you have 1 billion miles of driving on nothing but highways, your system really knows nothing about what it means to drive in cities. And so for us, we basically send the cars loose in San Francisco with highly trained drivers behind the wheel, and the system is running in autonomous mode and teaching us about the performance of our system. But in the background, it's recording all this data so that we have these crazy situations that we can feed into our models and teach them the difference between the little caricatures of people in this image and the real person. I don't know if you even see them, but there's a real person kind of standing in the middle there between the cutouts. And in the example below, which is, I put in a blog post I wrote a couple years ago, this kind of looks like, I'm not sure if this to you looks like a normal scene, or sort of if you put your engineer hat on, this looks like a complicated scene. But the point is, in this one of the problems with non-ML systems is it's really easy to maybe handle each one of these situations in isolation. Like I want to drive around I want to drive through cones, or I want to drive around a vehicle, or I want to avoid a pedestrian. But when you mix all of those together and you end up layering all these maneuvers on top of each other, anything that's based on a state machine or some historical way to solve this problem is going to get stuck and confused there. And so we need these situations both to understand the full scope of the problem we're trying to solve, but also to make sure that when you deploy this system that's full of machine learning models, the vast majority of the time, whatever it encounters on the road is going to be things it's familiar with, as in that scene is similar to what's in your training data set. And in the very rare cases, when it encounters something totally new, like maybe some variation of this scene, it is familiar enough to what the system has seen before that it can reason about something safe to do in that situation. And it never finds itself in a situation where it's something completely different than it's ever seen and with no sort of backup plan. So that's the reason we need really large data sets, and it drives some of the complexity. So when you have all this data, like I said before, it's completely useless to sit on this mountain of data if you don't know how to extract insights from it. So we've gone pretty far down the rabbit hole on doing things to basically use the minimal amount of human energy to extract the most insights out of our data. So what you've got here are some of these tools where, instead of having to draw a box around a person to say this is a person, we actually have ML models that assist the humans in doing this task of labeling. So it's sort of this lovely feedback cycle where the better the ML models get, the easier it becomes to label new data, and the human labor required to generate these data sets or insights from this data drops over time. And then on the bottom, you can see sort of a top-down bird's eye view of a scene, and the colored pixels represent LiDAR points. And the challenge there is, a 10-segment second of driving may have 100 individual frames, and the task is basically to label the same car across 100 frames of time. And so we have systems that basically automatically figure out, well, you labeled this car here, so you don't need to label it again. We'll sort of do the rest for you. And that's one thing that helps. And I think when you get to scale, these things become essential because of the size of the data sets you need. And if you're, the cost basically goes through the roof if you're not careful. So this is another vanity metric slide. I think it's, none of this stuff really matters. What matters is, can we solve the problem? But just to give you a sense of all the computation it takes to get this stuff done, I'm going to touch on simulation a little bit just because it's sort of very much related to how we use ML today, and will be very much more in the future. But if you have an autonomous vehicle system, basically you can think of that as a virtual driver. And it's not enough to put that driver through like a DMV driver test and say, is it good enough when you push out a software release? What you really want to know is, across the next 1,000,000 miles of driving, what is the estimated performance of that software going to be? And that's a really hard question to answer because of how diverse and crazy the world is. Like, how can you predict, when it sees those crazy scenes, how it's going to perform? And the answer is, we basically record everything we've ever seen and make sure that the new software does the right thing, which can also be used to train ML systems. And we also simulate a lot of stuff, situations that we haven't seen but could plausibly see. So you put those together and you get a pretty good coverage and a pretty good way to test the quality of your driving. And then the last thing on this list, this ML experiment platform, is really interesting. I want to paint a picture for you guys real quick and see if this resonates with any of you. How many people here are in academia or currently working for an academic institution? Okay, a few of you. So I think the workflow, especially if you're a grad student, is you're sitting at your desk. Maybe on your desk is a computer with a GPU that was donated by NVIDIA or something like that. And maybe you have $10,000 of cloud credits. And then you've got these open data sets that you can download from the internet that are pretty interesting, but they're small and kind of crappy still. And so that's the tools in your toolbox. And when you want to run an experiment or write your PhD thesis, you put all that together, you come up with an algorithm, and you hit train. That's sort of a gross simplification, but let's say you get to that point. And then you wait, yeah, that's your PhD thesis right there, that's it. And then you wait 2 weeks for an answer to come back if you have a really complicated model to download all your data and run it through the system, train a model, then evaluate your model. And so in my head, we're kind of living in the dark ages for machine learning experimentation and development. That's the equivalent of having like a C++ program and you want to compile it and you hit compile and it takes 2 weeks. Like imagine trying to debug that. That's basically the world we're living in right now, where the iteration cycle is on the order of days or weeks. So that's kind of insane. So well, here's a cool slide. I forgot about this one. So evaluation tools are important. Like these are another things. Like if you're sitting at your desk and you hit train and you get the output, it's probably like a big CSV file or whatever your data comes out at. So the next thing you want to do to iterate once you run that for 3 days or 2 weeks is go measure all your data and visually inspect sort of the things you didn't inspect, or look at the quality of your data set, or the diversity of your data set. And those things are really hard to do using off-the-shelf tools. So we've built a bunch of those, and it can be really interesting when you put it all together. But the reason we do all these things is not because they look cool and there's some eye candy, but because it helps us shorten that iteration time. We want to move out of the dark ages and into a world where you can iterate really, really fast on ML models to save the children. So I want to talk about what's next and sort of the trends, the general trends we're seeing right now, and what I want the world to be like for all of you when you're working on ML problems. So this one's pretty obvious. Like Moore's law is kind of dead in terms of CPU frequency, but not really in terms of cramming transistors on a chip. And I'd say like Moore's law is alive and well when it comes to neural network computation performance. We see all these custom chips coming out where it's not about faster clock speeds. It's not about more transistors, but it's like how you arrange those transistors to get more throughput for this types of compute workload. And so that's happening. And that means that we're going to build more complex models, because going back to the real-time aspect of self-driving cars, if you give me like 100 milliseconds to solve a problem and I'm an engineer, I'm going to like pack as much complexity into my model as I can before I run out of compute budget in that 100 milliseconds. And if you give me a bigger computer, I'm going to like make a more complex model to get better results. And usually, not always, but usually when you have a larger or more complex model, the data set that you need to sort of maximize the potential of this model before you saturate it becomes larger. And so you've got like 3 things that are on these exponential paths right now, which if you're not careful will sort of blow up the cost of the data sets, either collecting that data or more importantly, I think the cost to label that data. Right now, if you were to pay like an off-the-shelf company, or like the companies that exist today, if you're going to go to them and say, I want 1 million miles of driving, every bit of data from that drive annotated by humans, I think that would be billions of dollars, which is not tractable in any way, shape, or form. So I think the thing we're doing today, this is not necessarily the future, but what we're doing today is a lot more auto-labeling. And I don't know if that's the correct industry or academic term for this, but basically what I mean is you take the human labeling step out of the loop. And there's unsupervised learning, other ways to do this, but what I think is really interesting about driving is there's a lot of things you can infer from the way a vehicle drives. If it didn't make any mistakes, then you can sort of implicitly assume a lot of things were correct about the way that vehicle drove. And while we've got hundreds of cars out there and lots of people driving around, when the AVs are basically driving correctly and the people in the car are saying, you did a good job, that to me is a very rich source of information. I think you've seen other people in the industry do this. The simple example is when someone disengages an autonomous system, that's a signal. That's a label. There's probably something wrong happening at that point in time. Now, you don't know which of 1 million things could have gone wrong to cause that disengagement, so we do a lot of things with our human drivers to give them tools to tell us a lot more about what was happening. And that's a source of label, but that's still like kind of paying humans to do the job. What I think is really interesting is if you observe, basically use all the humans on the street around us as a source of ground truth or labels. So this little slide is kind of interesting here. This is one small slice of the kinds of things that can be done right now. At the top, you've got a map, and the sort of the brightness of the lines on that map represent how frequently we've observed human drivers following going down that particular lane of traffic. So it's basically like a heat map for where people drive. If we analyze that data, we can infer a lot about the correct way to make a left turn, or for the AV, but perhaps more importantly, what other people are likely to do, not just in a particular intersection, but more generally when they're making a left turn, it's not just this perfect parabola. Like people aren't like race car drivers where they're trying to hit the apex of the turn at the exact right speed. They do crazy things, and it's also dependent on context where other cars are on the road. And so that's another thing where if we were to write a heuristic-based system to do this, it wouldn't work. It will fail like the second it deviates from this very simple model that we have in our heads when we're writing that heuristic. And so you need sort of a more learned system to do this job. And if we were to try to pay humans to say, like, of the billion observations that our AVs have had of humans driving in San Francisco, can you go label each one of those, every car we've seen and what it was doing at the time? That's another really expensive endeavor. So if you're able to take human driving by observing the world around us and sort of infer from that using things like a map about what they were actually doing, you can build a system sort of like what you're seeing down below, where we basically haven't told the system how to figure out what other cars are doing, but just by observing literally billions of instances of other people driving, we can train the system to know what to do and or what other cars are about to do in a complex urban environment, even if there are no lane lines, and even if there are like cars, doing these crazy little social interactions, which is pretty cool. So basically, I think the conclusion from this is if you're a company and your business model is dependent on humans labeling your data, you're going to get crushed by the companies who are thinking about how to phrase this, how to reframe that problem in a way where they don't need to pay for those labels or have humans in the loop. The other thing. I talked about simulation briefly. I'll come back to that. So this is not a picture of San Francisco. This is actually a rendering from our simulation engine. And one of the really interesting things we can do with this is, right now I said we're bootstrapping the system by having lots of people drive lots of cars. But I think in the future, like systems like this, where we're still working on this, but as it gets better, we basically have this whole universe we've created. We actually call it the matrix, where the AVs live in this little universe. They don't know they're in a simulation. And the data that comes back in from that is getting so close to what the cars actually see out in the real world that I think we can put all these vehicles in a simulated world, kind of like an open AI gym, and just let them go. And we've started inserting other agents into the world. We have all these video game programmers who are like taking the AI from StarCraft and other games and dropping it into this little simulation. And so eventually what you have is this living, breathing ecosystem where the cars are sort of randomly encountering each other and using different flavors of driver profiles and getting themselves in these crazy, hairy, stuck situations. And we're basically using this as a source of entropy or fuzz testing to introduce new sources of data that we can generate purely synthetically without paying people to be on the road and labeling what's happening. And because it's in a simulation, we have perfect ground truth. We know actually where all the cars were, which means the labels that come out of this are far better than you can ever get from having people driving around and having humans try to approximate where cars and people are in that scene. So this is the future. You've got this like workflow from ML right now where you sort of create a model. Traditionally, you generate the labels, and then you train it, and maybe you like analyze what happened there, and you iterate on this loop. And I think that can take on the order of a few days to a couple weeks. What I'm looking for in the future is to basically go from an idea, like I want to build a model and I want to solve this problem. Here's the structure or for how it should be laid out. And I want to like hit compile. And I want to have in the background when that happens, a data set generated that is larger than anything that be collected and annotated today. The model trained and analyzed and basically continuously optimized until it's saturated in the same amount of time it takes to compile code. And so it's getting a little technical here, but the impact of this is anytime you can take an activity that takes on the order of days and weeks and compress it down to seconds, you're going to see a super exponential increase in sort of the quality of systems we're able to build and the types of problems we can solve. And I think perhaps most importantly, the barrier to entry for that person sitting at their desk in a grad school with an interesting idea, being able to explore the full potential of that idea and truly drive innovation. So I think that's where we're going, and we're building all of that at Cruise. Hopefully there's a takeaway here, which is deploying AVs at scale requires ML at massive scale. And today we're kind of still living in the dark ages, so you got to throw a lot of people and a lot of money at that to do it. It's a means to an end to solve this very important problem. But I would also end by saying, like, because of the things I've outlined today, I do think some of the best innovation is happening and some of the most powerful tools are being created inside of AV companies. So if you're not already working on AV, maybe this is a good time to ask yourself why. It says no sales pitches. This isn't a sales pitch, guys. This is a call to action. You need to save the children. You absolutely need to be working in AV if you're not already. I'm dead serious. Like, come on. You wake up in the morning, you know you're going to work, you're going to do the best possible thing with your skills as an engineer or whatever it is you do, and it's going to matter. And humans are only going to go from driving cars to not driving cars once. And so you're either a part of that or you're not. And that's for you to determine your legacy. So again, I know this isn't a sales pitch, but of course, if you do want to work at Cruise, we have Michael over here from our recruiting team who'd be happy to talk to you after this talk. All right, thank you guys.